Electric fans play a crucial role in maintaining thermal comfort. However, DC motor in-home fans often lack precise speed control, especially in low-cost design. Without feedback control, speed adjustment can be non-linear, sluggish, or unstable under varying voltage supply or load conditions. Thus, a closed-loop control system is needed to ensure consistent and smooth speed control regardless of external disturbance. Our objective of this project is to design a closed-loop system for the DC motor system, analyze the performance with our controller, and design a suitable controller to meet specific performance requirements as reduce setting time, minimize overshoot, and low steady-state errors.
The system modeling starts with mathematical derivation of the electrical system and mechanical system. Kirchhoff voltage law is applied to electrical system, while the conservation of angular momentum formula is applied to the mechanical system. The mechanical system formula is relating to the parameter of electrical system and substitute into the KVL equation and then get the transfer function. Next is the block diagram reduction, by reducing the forward transfer function in step 2 and then reducing the feedback transfer function in step 3. At the right side is the MATLAB transfer function lab script, and the defined DC motor constant is as shown.
Now I will present the time response analysis for the performance analysis. From the comparison table, both manual and MATLAB results show the consistent trend for the overdamped system. The MATLAB rise time of 1.1351 seconds is longer than the manual estimate of 0.402 seconds, showing that manual formula tend to underestimate due to high damping. And similarly, the MATLAB setting time is 2 point something second and compared to the 0.67 second manually, and both methods show zero overshoot, and this shows the system is non-oscillatory. Overall, the manual analysis and the analysis show the slow and smooth response with no overshoot and shows that the system is overdamped and stable behavior. The table compares the steady-state error value from manual and the MATLAB analysis. For steady-state error, the open-loop system have high error of 0.90031 for unit step input, which matches closely with the manual result of 0.909. This large error is expected from the Type 0 system, and after applying the PID controller, the MATLAB shows the error drop to just 0.00041, and this shows the controller effectiveness. The closed-loop system also performs better for the dynamic input, with final value reaching nearly 1, showing the accurate tracking. For stability, we have analyzed the open-loop system. The poles are both real and negative, located at negative 2.0025 and negative 9.9975. This confirms that the system is overdamped and stable. We also applied the rule for risk criteria with the first column showed no sign change, and the bar plot behind this will support this also. The bar plot also support the statement of no sign change, showing the stable low-pass behavior without gain crossover. The bar plot also confirms the open-loop system is stable and in the frequency domain with no resonance or crossover instability. From the root locus of the open-loop motor, the poles shift deeper into the left half plane, with gain indicating the system remains stable across the wide gain range. Overall, the both manual and MATLAB results confirm that the system is natural stability.
I'll be explaining about part 4, which is specifications design of the proposed system. For 4.1 objective of control system design, the open loop response of the DC motor system has poor performance with a setting time of 2.06 seconds, a rise time of 1.13 seconds, and a steady state error of 0.9 for a unit in step input. It suffers from slow transient response and is overdamped with no overshoot. It has long setting time and rise time. The system is type 0, meaning it has no integrated in the open loop transfer function, which result in high steady-state error. To improve transient and steady-state response, we define the following performance goal for the closed-loop system, which is a setting time of less than 1 second, a rise time under 0.5 second, a percentage overshoot of less than 5%, and a steady-state error approximately equals to 0. In addition, we aim to achieve a phase margin at least 50 degrees to ensure a closed-loop system will be robust and well-damped. These specifications form the foundation for our controller design using MATLAB control system toolbox and the root locus technique. Now let's move on to 4.2 controller design procedure using control system designer. To improve the dynamic and steady-state performance of the DC motor system, a PID controller with pseudo-derivative filtering was designed using MATLAB control system designer and a root locus technique. The prime model used in the design was defined to represent the open loop behavior of the DC motor. The compensator was constructed and tuned using root locus editor through the following steps. First, an integrator which is pulled at the origin was added to eliminate steady-state error for a step input, changing the system from type 0 to type 1. Second, a second pole was placed at s equals to negative 100 radian per second to implement pseudo-derivative action which filtered the derivative term. Third, two zeros was added in the left half plane to shape transient response and guide root locus branches. Fourth, the controller gain was adjusted to shift dominant poles to the desired region for target specifications. Fifth, once all performance specification was made, the final compensator was exported to the MATLAB workspace. The resulting controller transfer function is as shown below. The compensator was constructed in the control system designer using a standard PID structure with pseudo-derivative filtering. The compensator included, first, an integrator which is poled at s equals to 0 to eliminate steady-state error. Second, a real pole at s equals to negative 100 to implement a pseudo-derivative term. Third, a pair of complex 0 at s equals to negative 5.97 plus minus 2.56i to shape the transient response.
After designing and applying our PID controller, we tested the closed-loop system using MATLAB Control System Designer. The step response plot showed that our system met all the target specifications. The settling time improved drastically to 0.43 seconds, and the rise time dropped to just 0.0409 seconds. And there was a small 3.64% overshoot, indicating the system became slightly underdamped. Most importantly, the steady-state error was eliminated completely, showing that the controller effectively helped the motor reach and maintain the desired speed. Overall, the system became fast, responsive, and accurate, proving our controller design was successful. After designing the compensator in Control System Designer, we export it into a form of second-order transfer function. This structure reassembled a filter PID controller, and we wanted to extract the equivalent Kp, Ki, and Kd value for easier implementation. To do this, we use a derived equation based on comparing the compensator to the standard pseudo-derived PID form, which is shown in the slide. And to automate this calculation, we use a MATLAB script shown in the figure above, and this figure shows how we use the formula in the code to extract the gains directly from the compensator transfer function. As a result, we obtain the final PID value, which Kp equals to 215.62, Ki equals to 790.5, Kd equals to 16.55, and with the pole of A equals to 100. These gains were then used in the simulation to ensure real-time system stability and accuracy. I'll show a closed-loop system using a PID controller to regulate a dynamic plant. The step input serves as a reference, which is compared with the output to generate an error signal. The PID controller processes this error through proportional, integral, and derivative path, each two with respective gains. The derivative path includes a pseudo-derivative block to reduce noise. The combined control system is applied to the plant, and the output is fed back for continuous correction. The scope block displays the system response, helping to evaluate the controller performance in tracking the desired input. The system shows an underdamped step response with overshoot and slight oscillation before settling at the input value. So after the step change at t equals to 1 second, the output rises quickly, peaks above the bracket, and then stabilizes within a few seconds.